HYPOTHALAMUS Artificial Intelligence invites you to participate in the course. Artificial Intelligence in Financial Organizations. Industry 6.0 is the artificial intelligence genie out of the bottle. There is no turning back for this genius. Most people, including many scientists and experts in artificial intelligence, think that it is limited to generative pre-trained transformers models. In this way, this vision of AI has become popular. HY considers that today artificial intelligence is generative pre-trained transformers and mathematical programming. This is the main theme of HY's research. Digital Industrial Revolutions. Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. One of the most impactful changes occurs with the arrival of the Internet of Things, IoT, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models. It can be said that in Industry 6.0 all models work in real time, so that the world reacts distributed and online, for all IoT connected systems. For static systems, the methodology is also valid, but the world is dynamic. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we can talk about orchestration of swarms of cognitive robots, and living industrial ecosystems. These two terms are new to most people, including scientists, even though they date back at least 15 years. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies. And ethical and conscious governance, AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. There are 3 eras of modern mathematics aimed at handling computers. During this period, the basic mathematics that supports optimization does not change, but the technologies do. The creation of digital computers and iterative algorithms took place during Industry 3.0, in 1947. Until the arrival of Industry 4.0, the mathematics of algorithms grew, but it was from that moment that the complexity of formulations, and the use of solutions based on advanced technologies for large-scale optimization, generated the boom of modeling. This era includes Industry 5.0. The Industry 6.0 changes the mathematical modeling, giving rise to the orchestration of swarms of cognitive robots, and living industrial ecosystems. It can be said that the approach presented corresponds to a version of Industry 4.0, and that the change experienced until Industry 6.0 is very large, having affected the way of implementing mathematics, which is different from having changed mathematics. However, one of the most impactful changes occurs with the arrival of the Internet of Things, IoT, typical of Industry 4.0, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models, which are the ones that should be used today. Industry 6.0 focuses on the symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. Industry 6.0 is changing the mathematical modeling. Now we can talk about living industrial ecosystems, and orchestration of swarms of cognitive robots. This has led to the fact that, if desired, modeling in Industry 6.0 is autonomous, without human participation or coordination problems. The Industry 6.0 approach is applicable at all levels of decision-making, from planning to real-time, uniting all entities in the system. The case of greatest interest, or utility, is related to real-time applications. Due to the Internet of Things, the amount of data that a system receives tends to be infinite. This is appropriately handled by Industry 6.0. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. The swarm of algorithms make up an artificial brain that can be solved using Industry 4.0 or Industry 6.0 models. The latter seems to be the right thing to do. Living industrial ecosystems that act autonomously, making their own decisions, and reaching agreements with other living industrial ecosystems, to ensure the optimality of the living industrial ecosystems network. Coordination is done using a consensus algorithm, which are mathematical rules, like Lagrange's theory, and not a coordination problem. Artificial intelligence applied to companies in the financial sector. The course corresponds to a set of mathematical models aimed at supporting the decisions of the different agents involved in the services and operations of the financial services supply chain. The first module is related to financial services optimization. The models considered are Enterprise Risk Management, Integrated Assets and Liabilities Management, ALM, Risk Concentration and Optimization, Cash Flow and Working Capital Optimization, Global Liquidity Management, Settlement and Clearing in Financial Markets. The second module is related to optimization of logistics operations. The models considered are Banking Network Optimization, Relative Efficiency, Evaluation and Optimization, Human Resource Analytics, Debt Collection Optimization, Cash Management Optimization, Cash Transport Optimization, Catastrophic Risks. Artificial Intelligence in Financial Services Optimization. Module 1. The table, originally from IBM, presents several of the opportunities of optimization models in the financial sector. These are classified as Financial Risk Management, Operational Efficiency, and Customer Service. The table presents several of the models developed by HI, which may be useful to the financial sector. Economic value added by artificial intelligence. The evolution and prospects of artificial intelligence can be summarized as descriptive. It is the first step of artificial intelligence, or analytics. It is based on the research of databases to know reality, using SQL, structured query language. Predictive. Its objective is to know the most likely future scenario, which is done through pattern recognition. The most used methodologies are artificial neural networks, support vector machines, numerical simulation models, and advanced probabilistic models. Prescriptive, aimed at supporting decision-making, which is the purpose of the intelligence of the human being, to make the best decisions. The fundamental methodology is mathematical programming or optimization, in its stochastic versions. Unfortunately for society, this knowledge is not always considered as part of artificial intelligence, trying to turn predictive artificial intelligence into decision support systems. This is a serious mistake, since the two artificial intelligences are not comparable, neither in the degree of complexity, nor in the competitive advantage they have. However, both are necessary. Cognitive, highly automated machine learning and optimization solutions that get smarter over time. It is today's artificial intelligence, in accelerated evolution, both in the predictive field, where they have given rise to pre-trained generative transformers, commonly known as GPT, and in the prescriptive where they have given rise to artificial brains. Its support is the computational power provided by the Industry 4.0 revolution. HI's overall approach is to connect predictive analytical models with prescriptive ones, which involves an integrated, multidimensional holistic view of a company's entire supply chain. For example, in the insurance sector this usually involves two processes: claims analysis, and decision-making and financial risk control. The claims analysis based on artificial intelligence use multiple methodologies, which must be applied in the different steps of the study. Obtaining and analyzing databases. Metadata model design. Database loading. Relational database. Panel worktables. Customer characterization. Anomaly detection. Data envelopment analysis, DEA. Segmentation, clustering. Identification, machine learning, ML. Support vector regression, SVR. Advanced probabilistic models, APM. Classification. Customer modeling. Dynamic Markovian modeling. Markovian model of decision processes. Jeremy Shapiro, professor at the Massachusetts Institute of Technology, says, "The primary benefit of a decision support system, SSD, is the explicit reduction of costs and increased profits. The cost reduction of 8% made by our client is not atypical. In our experience, the integrated analysis of planning problems, using mathematical models, determines strategies between 3 and 20% cheaper. Many companies do not allow their positive experiences to be published, as they consider that an advanced decision support system gives them a competitive advantage. Corporate financial risk control. The Basel Accords are international standards that provide a common measure for quantifying banking risks and comparing them. This is very important in the case of internationally active banks, to avoid regulatory asymmetries. The international financial crisis of 2007 to 2009 led the Basel Committee on Banking Supervision to launch the Basel III Agreement in 2010, the essence of which is the macroprudential approach to supervision. Until then, supervision was mainly focused on individual entities. From there, the evolution of the financial sector as a whole is also analyzed, from a systemic point of view. Hence the need to control financial risk, at the level of the entities, and their conglomerates. Against the Gods, the remarkable story of risk, the measure of our ignorance. According to Peter Bernstein, in his book, Against the Gods, the remarkable story of risk. The revolutionary idea that defines the boundary between modern times and the past is the mastery of risk, the notion that the future is more than a whim of the gods and that men and women are not passive before nature. The essence of risk management lies in maximizing the areas where we have some control over the outcome while minimizing the areas where we have absolutely no control over the outcome and the linkage between effect and cause is hidden from us. Enterprise Risk Management, ERM. Holistic Risk Management, Strategic Risk Management, Enterprise Risk Management. Whatever you choose to call it, risk management is undergoing a fundamental shift within leading organizations, which are moving away from the individual departmental approach, silo by silo, to manage risk more holistically and coherently. ERM is a scientific approach to shaping risk. The approach to shaping risk relies heavily on operations research methods, such as applied probability and statistics, stochastic simulation, and portfolio optimization. ERM is a rigorous approach to quantifying and managing risks, from all sources, that threaten the achievement of an organization's strategic objectives. ERM identifies those risks that correspond to opportunities that allow the exploitation of competitive advantages. Its objective is to increase the wealth of shareholders. Stavros Zenios claims that ERM is strategy that aligns the firm's businesses with the risk factors of its environment in the pursuit of strategic objectives. ERM is based on the conceptual structure, organizational approaches, and analytical tools that integrate market, credit, liquidity, operational and business risks to achieve the objectives of the organization. Assets and Liabilities Management, ALM. ALM allows aligning the environmental risks that are reflected in the balance sheet and the income statement, both on the asset and liability side. ALM correlates all an organization's risks in such a way that the total risk exposure faced by the organization is not reduced or increased, as is the case when risk correlation structures are ignored. ALM is defined as the management of assets and liabilities supported by stochastic optimization techniques to obtain adequate performance, and this is achieved by structuring processes for the synthetic generation of probabilistic scenarios that are considered in the algorithmic procedures of multi-stage stochastic optimization. ALM is defined as the management of assets and liabilities supported by stochastic optimization techniques to obtain adequate performance. This is achieved by structuring processes for the synthetic generation of probabilistic scenarios that are considered in the algorithmic procedures of multi-stage stochastic optimization. The first stage of stochastic optimization, based on predictive analytics, is related to the probabilistic characterization of the YH vector that represents the variables associated with the random scenario, that is the decision environment. The second stage, based on prescriptive analytics, is related to the selection of the vector X that represents the decisions supported by the model. The objective of the mathematical problem may be minimize/maximize expected value, mean variance, minimize maximum cost, maximize minimum income, or optimize the expected value with restricted risk. ALM models produce as a result the financial and fiscal statements of the organization. Income statement, balance sheet of assets and liabilities, and cash flow. Professor John Mulvey, at Princeton University, states, "In the end, we can turn to engineering for ideas concerning the proper level of risk protection. For instance, aeronautical engineers optimize the shape of modern airplanes by minimizing weight and maximizing strength. Computer simulation or optimization systems are employed. The Boeing 777, for instance, was largely designed with the aid of computer analysis. An important part of this analysis is stress testing the airplane in conjunction with severe conditions. The computer flies the airplane through these scenarios to evaluate the system's ability to withstand the stresses. In a financial simulation, we seek similar goals to evaluate the investor's ability to withstand economic downturns. For example, a U.S. pension plan surplus will likely drop during a recession with lower equity returns and lower interest rates. The simulator will give information regarding the accompanying contributions. A long-term investor should be able to withstand these periods. Multi-stage financial planning systems are helpful in gaining an understanding of future risks and the investor's planned responses." ALM experiences. The image presents a list of global companies in the financial sector that use ERM and ALM models. Yasuda Fire and Marine Insurance is a Japanese insurance company established in 1888. In 1991 it had 685 offices in Japan and 22 offices in the rest of the world and managed a total of $26.2 billion American dollars. In 1991 it was the second largest Japanese insurance company and the fifth worldwide. In 1988 Yasuda hired the Australian company Frank Russell to design and implement a financial planning model that came into operation in April 1991, generating profits of $7,900,000 American dollars in the first 2 years. The Russell-Yasuda Kasai model is at the core of all asset liability work for the firm because the traditional models such as Markowitz mean variance cannot cope with the complexities of the business. A well-known global company that provides actuarial and risk management consulting services with more than 8,000 employees in 80 offices in 23 countries, uses an integrated asset and liability planning system for pension administration decision-making. This system is called CAPS-Link, Capital Market Linkages. The CAPS-Link stochastic optimization model relies on an economic model of stochastic differential equations for the generation of projected scenarios for economic factors, and for the return on assets. The scenarios cover planning periods of 10 to 40 years. The stochastic optimization model dynamically determines the distribution of assets and liabilities over all the scenarios analyzed. Based on CAPS-Link, Tor Parents provides advice to client companies based on personalized investment analysis that allows them to measure the risks of different pension plans from multiple points of view. This approach has been implemented in 12 countries in Europe, Asia and North America. Federal National Mortgage Association, Fannie Mae is a company created, sponsored and regulated by the American state that provides financial products and services for American citizens of medium and small incomes. There are two main lines of business: mortgage guarantee business, and mortgage investment business. By the end of 1990, the investment guarantee portfolio had been in operation for more than 50 years and totaled more than $117 billion, while the guaranteed portfolio had been in operation for 10 years and totaled $300 billion. Fannie Mae uses the Asset Liability Management Strategy System, ALMS, to support decision-making regarding the management of a highly leveraged portfolio of home mortgage assets. ALMS employs a combination of Monte Carlo simulation and pricing options models to estimate the payback period probability distribution function for each asset and for each obligation considered in the portfolio optimization model that maximizes the utility of the owners. Pacific Financial Asset Management Company, a large Californian investment company, uses the SMART, Surplus Management and Risk Technology, system, based on a nonlinear stochastic optimization model, for the distribution of the portfolio of financial assets that support the pension plans. The critical factor is balancing the risks and potential gains of strategic decisions related to projected liability movements. This approach allows for the management of risk in a more comprehensive and realistic way. The optimization model extends Markowitz's mean variance theory to manage assets and liabilities in such a way as to preserve the organization's wealth, defined as the market value of the assets minus the present value of the liabilities. In 1994, SMART has been implemented in personal computers, giving it great coverage capacity within the organization, allowing institutional investors to advise on how to distribute their investment among different types of assets, stocks, inventories, bonds, real estate, derivatives and others. Case: Insurance Express, a hypothetical insurance company in Latam. A client of HY. In 2005, Insurance Express established the following project. Challenge: develop mathematical models for the financial risk management business of transport, life insurance, and other lines of business of Insurance Express. Solution: development of a theoretical framework with the corresponding technological implementation, through an optimization model to support a risk measurement and control system, in accordance with the standards established by the financial superintendents for the insurance industry. Implementation of a non-anticipative stochastic optimization following ALM, asset liabilities management, methodologies. Result: implement the ALM optimization model on an Insurance Express server. Two important results of the model are presented below. Due to the bi-criteria nature of the problem, ALM is the means to generate expected benefit versus Pareto risk curves, which is the synthesized information that decision makers require as support. Under this conception, mathematical models do not make decisions, it is the executives and managers of the company who make them. The VAR curve, rose, is non-convex, due to its mathematical characteristics. The C-VAR curve, blue, is convex and therefore is more appropriate for doing the studies. Risk profiling is another of ALM's objectives. 3 risk profiles are presented in the image. Risk averse, dotted line, the investor regulates his losses, to minimize them without importing the profit. Risk prone, blue line, the investor maximizes the expected profit, without considering the risks, and rational, black line, the investor uses the scientific method to obtain a profile, which significantly reduces losses, in exchange for slightly decreasing the expected profit. Sovereign Assets and Liabilities Management, SOM. ALM has been extended to Sovereign Asset and Liability Management, SALM, which focuses on identifying and managing financial risk exposures of the public sector, to preserve a strong balance sheet that supports a sustainable policy trajectory and economic growth. In general, the sovereign balance sheet includes the assets and liabilities of the central government, municipalities, pension funds, state-owned enterprises, and central bank. Management measures may also include off-balance sheet instruments and policy commitments. This approach involves monitoring and quantifying the impact of movements on economic and financial variables, including exchange rates, interest rates, bond issuance, inflation, government policies and commodity prices, sovereign assets and liabilities. It also manages vulnerabilities related to national assets and debt, or regional, or macro-sectoral, in an integrated manner. Risk concentration and optimization. The concentration of businesses, or investments, in one market segment, has been identified as a major source of risk, for organizations of any kind. Traditionally, studies based on classical portfolio theory address the problem of concentration indirectly, since their main concern is the diversification of assets through mean variance schemes, or similar, but without providing a measure of concentration, nor an explicit relationship with the risk of the portfolio. In the case of credit risk, agents usually apply rating techniques based on the opinion of experts, on the degree of concentration in different segments, to obtain an indicator of credit concentration. The indicator obtained is valid in cardinal and hierarchical terms, but does not correspond to a direct measure of risk, which can be translated into potential losses, or value at risk. HY has developed 2 types of models for the measurement and control of concentration risk, formulating the following. Concentration measures based on the Herfindahl-Hirschman indicator, and optimization models to determine the best distribution of the portfolio of assets and liabilities, in terms of risk concentration. Examples of concentration dimensions are economic sectors, geographic regions, genres, ages, professions, foreign exchange, actions, agricultural products, and business lines. The mathematical methodology for managing risk concentration provides explicit formulas for measure the corporate risk associated with concentration, and accurately quantify policy actions to maintain the organization's capital reserve adequacy. In addition, the model provides simple means of determining the effects of correlation and concentration of the risk portfolio. The methodology works based on individual limits for each dimension of risk, and the Herfindahl-Hirschman index that are related to concentration, and the measures are subject to the same limit. Any indicator can be used as a normative instrument. Process optimization makes possible to determine the optimal distribution of risks that reduce concentration risks in financial institutions. Global supply chains and financial modeling. The integration of mathematical programming models, better known as optimization, is since mathematical programming is a standard for the modeling of physical systems and business processes. This is because the joining of mathematical programming problems generates a new model, or a variation of an existing model of mathematical programming. In the case of integration of production and finance, there are originally two models, sales and operations management, SAND-OP, and asset and liabilities management, ALM. These models can be summed together, resulting in a mathematical model containing the constraints of the two models, forming the SAND-OP, ALM model. The user will have three models, the original ones and the integrated model. The integration process can be conceived in a coordinated way where the S&OP model generates results, production and sales, which must be transformed into financial results, in the ALM model, to produce the financial statements of the organization, the control of which is the true objective of a company. The traditional thing is to coordinate the two models, in such a way that the production model feeds the finance model. This process has no feedback, and therefore the financial model can be an Excel workbook. The modern vision is to integrate the two models into a single model, which has important advantages. It implies a feedback between the two systems. It is then possible to introduce financial constraints into the production model, for example, cash flow constraints, and the financial variables can be introduced as part of the objective function, for example, the value of the firm at the end of the planning horizon. This model achieves optimal solutions, which are not obtained with the coordination of two separate models. From a functional point of view, the integration of the models implies the direct participation of the board of directors in the planning of the company. The balance of international flows is one of the important benefits of the SAND-OP, ALM model in a global company. Without the integrated planning model, each expenditure center will make decisions independently, or coordinated in pairs, and money transfers will not be optimal, paying unnecessary transfer costs. Operating with the SAND-OP, ALM model, a virtual netting center must be established to minimize the cost of transactions, respecting operational and financial balance restrictions. The benefits derived from comprehensive liquidity planning are centralized coverage strategy, visibility of total exposure, reduced hedging and risk exposure costs, and reduced payment processing costs. Settlement and clearing in financial markets. A clearinghouse is a financial institution created to facilitate exchange, such as clearing payments, securities, or financial derivatives transactions. The clearinghouse is located between two clearinghouse member firms, a buyer and a seller. Its purpose is to reduce the risk of a member firm failing to meet its commercial settlement obligations. For the security of the operation, from its origins, the time that the clearing of transactions lasts, the money and the values of the participating firms are locked, which implies that the cost of operation depends directly on the settlement algorithm used. The existing computational power allows this settlement process to be almost real-time, reducing capital requirements for participating companies. Case: Indival Clearing House. The Instituto para el Depósito de Valores, Indival, is a successful experience. Indival is the central securities depository of Mexico. It is the only Mexican institution authorized to execute the activities of custody, administration, clearing, settlement, and transfer of securities. The article. Indival develops a new operating and settlement system, using operations research. Winner of the Franz Edelman Prize in 2011 presents the experience reported by Indival. The savings from financial guarantees are obtained through the Securities Settlement System. SLV, implemented by Indival, in 2010, as part of a project for the construction of a safer and more efficient operating system. The objective of the system is to use smaller amounts of cash and financial assets in the settlement process of the Mexican market, within an appropriate period, using a linear programming model for the clearing of securities and cash. The SLV was launched on November 14, 2008, after 3 years of business process design, complex software programming, and 9 months of exhaustive daily testing. The benefits in reducing liquidity requirements were 52% in the case of cash, and 26% in the case of securities. These benefits are directly linked to the speed of the SLV algorithm. As the higher the speed, the execution time will decrease and the number of settlements per period will increase. Artificial Intelligence in the Optimization of Financial Logistics Operations. Module 2. Planting and Climate Risk Management. The biggest problem for insurance companies is that they must intervene in the process of sowing and harvesting of agro-industrial products, since the management carried out by the operator derives the risks that the financial company may end up assuming. Ignoring this situation can imply a significant reduction in economic benefits. Additionally, the high geospatial correlation of the climate must be considered, which increases risks, having to look carefully at the concentration of risks in a region, or in a type of product. The image shows the plantation planning and risk management process, and the models involved. ENOS, projection of hydroclimatic variables DEM market, projection of financial and market variables POP, optimization of the planting, and ALM, assets and liabilities management. Seismic risk management. Case, Italian Tuscany. The document. Earthquake risk management via stochastic optimization, a case study for an Italian region. It describes a stochastic model of spatial dynamic optimization, which considers the complexities and interdependencies of catastrophic hazards, has been customized to incorporate the geological features of a region, seismic hazard parameters, and the vulnerability of the built environment. The model can analyze the interaction between investment and mitigation measures and risk-sharing measures, pays attention to the evaluation of a multi-pillar seismic loss propagation program, involving the central government, and mandatory insurance. The model can analyze multiple policy options, to develop insurance equitably, and their effects on insurance premium, and reserve funds. To analyze system stability, EASA uses a strong connection between non-differentiable stochastic optimization, and risk measures such as value at risk, VAR, and the probability of bankruptcy. The study was developed for the Tuscany region. Even considering that Tuscany is not among the most dangerous regions with respect to seismic activities, the case is quite representative for the methodological approach, since all the results have been normalized to refer to monetary units. The choice of Tuscany was determined because the Institute for Research on Seismic Risk of the Italian National Research Council had already made models and had data from a previous study. This data has been incorporated into a Monte Carlo seismic event generator, which simulates the occurrence of earthquakes affecting the region, calculates attenuation according to geological characteristics and, finally, determines the acceleration in the ground in each municipality. The stochastic spatial dynamic optimization model has been customized to explicitly incorporate the vulnerability of the built environment, with data on the number and type of buildings in each municipality in the region. In the first phase, the study was limited to analyzing policy options for an insurance program. In the second, the interaction between investments in physical mitigation, retrofitting and risk-sharing measures is investigated. This methodology can be applied to the process of optimizing decisions to ensure shopping centers, housing developments, large-scale civil projects, or other facilities, whether it is from the point of view of the insurance company, maximizing profit and controlling the risk assumed, derived from the concentration, or from the customer's point of view, avoiding the concentration that could lead to the bankruptcy of an insurance company, that is, controlling the risk they assume. Optimal design of the banking network, branches, ATMs, offices. Model aimed at establishing the optimal network of bank assets. Its use is important to make the following decisions: location of new facilities, and relocation of existing facilities. The second decision is typical of the processes of buying, or merging, banks that already have their own infrastructure, and that by joining the two banking networks may present oversizing of the network. Modeling may include optimizing workforce location. Relative efficiency of bank branches, evaluation and optimization. DEA is used for high-to-supply services of evaluates productivity of process units in several industries on demand. DEA allows to establish efficient Pareto curves for non-homogeneous production units, bank branches, hospitals, market agents, employees, that produce different types of outputs or products and use multiple types of inputs or resources. In the field of economics, efficiency refers to a judgment about the relationship between the means used and the ends obtained. A technique, an office, a procedure, an organization, a person or a production system, and more general a decision-making units, DMUs, will be efficient if given an availability of inputs, it is able to produce the maximum possible number of outputs or, alternatively, if it uses the least number of inputs to achieve a certain level of outputs. Bank DEA is a model aimed at establishing the relative efficiency of people and facilities, offices, ATMs, persons, of the financial, industrial. Its use is important to make the following decisions: classification of facilities and people based on their relative technical efficiency. Definition of efficiency standards. Improvement of the working conditions of the production units, offices, ATMs, people, according to the most efficient units, and closure of production units. The non-parametric efficiency analysis data envelope analysis, DEA, was developed by Charnes, Cooper and Rhodes in 1978 and has been used to estimate the efficiency of decision-making units, DMUs, in various fields of application. DEA is an efficiency measurement model, supported by linear programming techniques, which aims to evaluate the relative efficiency of different homogeneous DMUs. The application of a specific model for each DMU evaluated allows us to obtain a measure of efficiency for each DMU. The basic idea of DEA, which is generally an extension of the traditional ratio analysis for the case of multiple inputs and outputs, is that, to analyze the efficiency of a particular DMU, it is considered efficient if no other DMU is capable of produce a higher level of outputs using the same inputs, or if produce the same level of output from a lower level of inputs. Thus, it will be possible to distinguish those units that behave efficiently from those that are not, so that efficient units define the efficient boundary. DEA efficient frontier includes the following points: O. Projection with the output-oriented model, B. Projection with the base-oriented model, and I. Projection with the input-oriented model. DEA allows the calculation of technical efficiency indices by solving multiple linear programming models based on the data that represent the set of DMUs to be evaluated. The objective is to obtain a scalar that represents the minimum proportion to which the consumption of inputs can be reduced without reducing the amount of production produced. The greatest advantage of DEA is its flexibility, in the sense that it imposes less restrictive conditions on the reference technology and because it adapts to multi-product context with relative simplicity. Another advantage is that it allows all inputs to be related simultaneously to outputs, making it possible to identify which inputs are being underused. A limitation that should be mentioned about the DEA is the conceptual difficulty of separating the effects of environmental variables, uncontrollable, from the effects that result due to differences in the management of inputs. The main DEA models are CRS, constant return to scale, input-oriented models, with constant returns to scale. VRS, varying return to scale, output-oriented models allowing variable returns. NIRS, non-increasing returns to scale, output-oriented models allowing constant returns to scale, and FDH, free disposal hull. Cash management optimization. The image presents the entities involved in cash management. The problems that must be faced are: on banks and financial institutions, localized cash demand projection, bank reserve requirements, locating cash inventories, and contracts of carriage; on value transporters, optimized distribution and collection routes, and assignment of crews following safety criteria. The specific objectives of the modeling are: ensure that the bank's cash is managed in an agile and efficient manner, obtaining savings in its transportation and processing; manage the supply and collection of cash at branches, customers and ATMs, in an agile, timely and efficient manner; to make forecasts and predictions for the timely and efficient provisioning of the bank's branches, funds and ATMs of the bank; provide the necessary technological and functional tools to manage the cash of the bank's branches, ATMs, customers and funds, optimizing the number of trips made by the value carriers, the use of denominations, banknote qualities and the supply forecast, and generate and guarantee the sending of reports that allow the bank to demonstrate the traceability and status of the process in each of its stages and the behavior of the management indicators to ensure compliance with service levels. Cash transport optimization. In 2020, HY implemented a solution for vehicle routing and cash transport. The characteristics of the project are: challenge, to implement an informatic tools to optimize its collection/distribution operations of cash and securities. Solution, design and implementation of a set of mathematical models to define routes of client services, assign vehicles to routes, and assign crews to vehicles. Result, deliver the models to the client who implemented the models in its information technologies system. Debt collection analytics. Case, GE Capital. As an example of this application, reference is made to the paper Managing Consumer Credit Delinquency in the U.S. Economy, a multi-million-dollar management science application. GE Capital, a subsidiary of General Electric Company, provides credit card services in a business that exceeds $12 billion annually. In 1989, GE developed the payment system, which is a DSS aimed at making the optimal allocation of resources in the collection process. Payment has changed the way GE handles the groups of delinquent customers in its portfolios at its 300 retail stores. It is based on management science methodologies. Payment can be credited with the $37 million per year in which the losses of the portfolios of retail stores have been reduced. With payment, it currently costs less to collect more. GE Capital earned $37 million of American dollars annually from payment. The image presents the debt collection optimization process. Human resources analytics. In general terms, the workforce optimization model must establish the balance between the demand for actions by department and the assignment of positions to execute these actions, having as a reference to minimize the cost of payroll. Part of the process is related to establishing the demand for actions, which is an indirect function of the level of operations of the departments, which is initially transformed into demand for processes, then into demand for activities, and finally into demand for actions. Allocation of human resources to mobile workstations. Mobile human resources optimization. Challenge, to solve the problem of human resource allocation considering a geospatial dynamic demand of human resources. Solution, design and implementation of an optimization model for human resource allocation considering a geospatial dynamic demand in which services changes throughout the days and times of the day over the space. The solution of the model: minimize allocation costs, increase the level of customer service, and generate employee comfort. The model generates the timetables for each human resource. The solution developed by HY is composed of 5 specialized mathematical models that support the bank in making optimal decisions for strategy, tactics, and operation. One model is oriented to the knowledge of the stochastic process that governs the behavior of demand. DEM, probabilistic characterization of the behavior of the demand for services that bank branches must serve. And 4 models to the planning of the supply chain of cash. LAY, optimal design of a branch, or of a set of branches, according to the demand to be met. PTA, optimization of human resources hiring for the medium/long term. POD, scheduling of staff assignments, roles, to branches to meet short-term demand. And PHC, assignment of people to attend to the planning carried out in the previous model. Optimization of the organization's payroll. Challenge, develop a mathematical model to determine the optimal allocation of the workforce. Solution, design and implement a set of mathematical models that focus on increasing the company's productivity in terms of human talent. The solution determines the optimal allocation of labor, reallocates human resources, creates jobs and profiles, and selects the people who will remain in a process of reducing human resources. Result, the model developed by HY was delivered to a human resources consulting company, which provides professional services to its clients.
WFO, Workforce Optimization, está orientado a establecer la nómina óptima de una empresa. Resuelve las siguientes preguntas. ¿Cuántas personas debe tener la empresa para llevar a cabo sus actividades? Discriminadas por sitio y por departamento. ¿Cuáles personas de la nómina actual deben mantenerse y cuáles deben despedirse? La solución a este problema se obtiene mediante modelos de optimización.
In general terms, the workforce optimization model must establish the balance between the demand for actions, or activities, by department, and the assignment of positions to execute these actions, having as a reference to minimize the cost of payroll. Part of the process is related to establishing the demand for actions, which is an indirect function of the level of operations of the departments, which is initially transformed into demand for processes, then into demand for activities, and finally into demand for actions.
Capacitación de la fuerza laboral. La capacitación es una tarea clave para garantizar que los empleados permanezcan en un nivel de habilidad, que conduzca a la productividad y al logro de los objetivos de la organización. Sin embargo, la capacitación es una inversión costosa. Por lo tanto, los recursos asignados deben utilizarse óptimamente, para equilibrar los recursos disponibles con los objetivos buscados.
Epilogue. According to Warren Buffett, financial risk is established in the fact that people don't know what they're doing. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.